Hello everyone and welcome to the channel. So in this particular video we are going to talk about thermodynamic equations of states, and you know that there are two thermodynamic equation of states. So what I'm going to do is, first of all, I'm going to explain you what this thermodynamic equation of state is and what that, like, I'll just tell you the equation. Then we'll go into the technicality of the equation. That means how that equation changes for the different cases, like for real gas, for ideal gas. And then at the end of the video we'll take some questions from the previous year of CSIR-NET exam, and we'll see that how you can apply these thermodynamic equation of states over there in order to get the answers, right? So this is going to be very interesting video, and it's going to be very important video, right? So if you are watching this particular channel for the first time, if you have not subscribed to the channel, do subscribe to it. And yeah, let's continue with the topic, right? So you know that the equation of, like, the thermodynamic equations, right? We have discussed about that in my previous two videos. I have given you the explanation of the basics, and then we have discussed about the first law of thermodynamics. Now, from the first law of thermodynamics, the differential form of that first law of thermodynamics is something like this. That is, du is equals to, you have TdS minus PdV. Now, this TdS comes from the value of dq. Okay, this actually has been taken from the second law of thermodynamics. So first and second law of thermodynamics, like when you combine both of them, you are going to get something like this. This is the equation which you get, right? So I hope all of you know this equation. This is a very familiar equation and a very simple equation, right? So from this particular equation, on applying the different thermodynamic relations on that, and also applying the Maxwell relation, you will get thermodynamic equation of state. Okay, now before continuing into this particular thing, if you have not watched my video on Maxwell equations, how to find out Maxwell equations and how to, like, a shortcut trick I have actually given to find out Maxwell relations. So if you don't know about that, I'll give you a link over there in the I button, so you can just click on that link and you can watch that particular video, right? Now let's continue with our particular part. So basically, how it has been derived is, first of all, you just differentiate this equation with respect to v and keeping t as constant. So what you have to do, you have to differentiate. Okay, so differentiate with respect to v and keep t as constant. Okay, means the temperature has been kept constant and you are differentiating with respect to volume. So you'll get del u by del v at constant t, that will be equal to t, because t is constant, and then you will be having del s by del v at constant t minus, and if you differentiate this dv, right? So you are going to get dv is equals to, like, dv will become 1 itself. So fine, so you'll be getting just p over here. All right, now we'll use Maxwell relation, and using Maxwell relation, I'll just write down over here in the side that del s by del v at constant t, using Maxwell relation, that is actually equal to del p by del t at constant v. Okay, so that's the relation between these two, using the Maxwell relations, right? Or using the thermodynamic square, you can get this thing. Now if you put it over here, so what you are going to get is del u by del v at constant t, that will be equal to t. I'm just going to substitute its value over here, so that becomes del p by del t at constant v minus p. So this is going to be, or this is going to be called as the first thermodynamic equation of state. Okay, so what it is, this is nothing but first thermodynamic thermodynamic equation of state. All right, so this is very simple, very easy thing, right? You have just taken the combined form of your first and second law of thermodynamics, just differentiated with respect to v and kept t as constant. Now as simple as the equation looks like, it has a lot of applications. Okay, so first thing which I should tell you is that this particular thing, that is del u by del v at constant t, which is called as, you can state it like this, that the change in internal energy with respect to volume at constant temperature, right? So the change in internal energy with respect to volume at constant temperature, this is what you get from the left hand side, and this is also expressed as internal pressure. Okay, it has been seen that it has the this particular equation, this left hand side has the dimension of pressure. Now how to assign dimensions and all, so I'll just go into a little bit basics of your, dimension analysis, right? So dimensional analysis says that if you have three terms, let's say a is equals to b plus c or b minus c, whatever it is, if these are the three terms related to them like this, okay, a, b and c can be any equation or any terms, okay, any terms, right? So the dimension of A will be equal to dimension of B and will be equal to dimension of C. Okay, so if they are in plus also, then also the dimension of all of them has to be same. In the same way, keeping the same thing over here, just applying the same thing over here, you can say that the dimension of this particular part will be equal to the dimension of this particular part, and that should be equal to the dimension of P. P is pressure, right? So that's what we can say, that dimension of del U by del V at constant T uh, is equal to dimension of, like, dimension of pressure. Okay, so what we can assume, or sorry, what you can uh, like what we can interpret from here, that the dimension of this del U by del V at constant T has a dimension of pressure. So it is also sometimes represented as pi. Okay, so if you represent it as pi, so what your equation is going to become, that pi is equals to T del P by del T at constant V and minus P. So it's the same thing, I have just expressed it as pi, that's all. So if pi is it, so that means pi has a dimension of pressure, and pi is nothing but that's the same thing, del U by del V at constant T. Okay, so that was all about your first law of, sorry, that was all about the first thermodynamic equation of state. Now let's try to let's try to see it, what and how it changes for different cases, like for ideal gas, for real gas, what will be the changes in the values. So let's look upon that. All right, so I have just written this first thermodynamic equation of state over here, just to make sure that, yeah, just for the reference thing, right? Now let's take it for the ideal gas. Okay, so for ideal gas, what we are going to get? So for, let's say we are doing for ideal gas. So we are going to talk about the ideal gas. So we know that the ideal gas has the equation PV is equals to nRT. Now I'm taking for 1 moles, but just to make the things easier, so it will be PV is equals to RT, or I can say that my P will be equal to RT by V. Okay, that's what my equation for, from the ideal gas I can interpret the value of P. Now I can just substitute its value over here, right? Just to get this particular part, just to solve this particular part. What I have to do? I have to differentiate with respect to T and keep my V as constant. And that means if I do that, so I'll be getting del P by del T at constant V. This actually I'm going to get, I'm just differentiating this equation, okay, with respect to T and keeping V as constant. So if V is constant, R is already constant, so these two things are not going to differentiate, these two things will not be differentiated, so that can be taken outside. If you differentiate T with respect to T, so obviously you are going to get 1, right? If you differentiate X with respect to X, that means if you differentiate d by dx of X, you'll get 1, right? In the same way, if you differentiate T by with respect to T, so again you are going to get 1. So the same thing I'm going to apply over here. So that means what? That the value of del P by del T at constant V is nothing but R by V. Alright. Now I'm going to use this thing to substitute over here and to solve. Okay, so just substitute it over here. So you'll be having del U by del V at constant T will be equal to, now this T is already here, so I'll just put T and I'll put the value of it. So it is nothing but R by V, okay, and minus P. Now look at this particular value, what this RT by V is. This RT by V is nothing but equal to P. So I can substitute that value also again, right? So that means my del U by del V at constant T is going to become P minus P, or it is going to be 0. So that's what some like earlier ones in CSIR-NET exam it was asked, like for ideal gas, what will be the value of del V by del U by del V at constant T. So this is how it has to be solved, and it will be equal to 0. Okay, I'll be showing you the quotient at the end of the video, don't worry about that. But yeah, this is how it will be solved, and that's how you get the value to be 0. All right. Okay, so this was for the ideal gas. Now we also have one more type of gas called as the real gas. So now let's look upon the same thing for the real gas. Alright, so we'll talk about real gas, right? So real gas means the one which follows the van der Waals equation. So the equation I'll just write down. The van der Waals equation is given by P plus A upon V square, and in the bracket you have V minus B, and that is equals to RT. Okay, that's the equation. Or you can calculate the value of P. You can just multiply and take the other things to the other side, and in that particular way your P will be actually equal to RT upon V minus B. Okay, this is going to be in one bracket, this is V, and minus A upon V square. So this is going to be the value of P. So you got the value of pressure, right? Fine. So now what you have to do, just differentiate this with respect to t, and just differentiate it with respect to t, just to calculate the value of del p by del t at constant v. So the same thing we are going to do. So I'm going to calculate del p by del t at constant v. So when you will differentiate that, r and v upon b, that will be considered as a constant, right? So that will come outside, and if you solve this, so this particular part will be like, only you will get r upon v minus b. Again, the differentiation of t will be equal to 1. So this will be the one of the part, and minus here, if you differentiate it with respect to t, keeping v as constant, so its whole of this thing is going to be a constant term, right? So this is going to be a constant term, so that means the differentiation of a constant is actually 0. So you'll get just 0 over here. So just substitute it over here in this particular equation. So what I am going to get is del u by del v at constant t, that should be equal to, now t I already have, so it will become rt upon v minus b. Okay, I have just substituted its value over here, and minus p. That's what I will get. Alright, so what I can do now, I can just put the value of p from this to this, right? I can just put the value of p from here to here. From this equation 1, I can just put its value over here. So my del u by del v at constant t is going to be rt upon v minus b, and if I put the value of p and I open the bracket, so this will become rt upon v minus b, and this negative sign will make this negative sign positive, so I'll get a upon v square. Now you can see that these are the same terms, they will be cancelled up, right? So what you will get is this, that is del u by del v at constant t is actually equal to a upon v square. So for real gas, you have del u by del v at constant t is equals to a upon v square, whereas for the ideal gas, you have it equal to 0. So these are the two very important equations which you should know. Okay, it can be asked anytime in the CSIR-NET exam. Fine. So, or you can also say that it's pi, right? It's pi at constant t, or pi value. For n moles of gas, you just have to multiply with n over here. So it will be na upon v square. So that's it. That's the only thing which will change for n moles of gas. So this was the application part of your first thermodynamic equation of state. Now let's jump to the second thermodynamic equation of state. Alright, so now we are going to discuss about the second thermodynamic equation of state. Now you all know about this equation, right? dH is equals to TdS plus VdP. Okay, now this is the equation which relates your enthalpy with entropy and with pressure and volume. So this has been taken from the first law of thermodynamics, the enthalpy equation of the first law of thermodynamics. The equation is dH is equals to du plus Pdv. Okay, and using that particular equation, and also the first equation of thermodynamics, it says du is equals to dq plus dw, and your dq is equals to tds, so that you can put it over here, and dw is nothing but pdv minus pdv plus vdp. So you can use that and you will calculate it, and in that case you will get this equation. So I just told you that how you can get it, but yeah, this is a well known equation, so I hope you guys remember this, right? So we just use this equation to get the second thermodynamic equation of state. So let me just erase these two, because these we don't know for these we don't need actually for the rest of the work, but yeah, the one which we need, I have just highlighted that. Okay, next what you have to do is you just have to differentiate the equation with respect to pressure. Remember, to get the first equation of first thermodynamic equation of state, you have differentiated with respect to volume, keeping T as constant. Here again you are going to differentiate with respect to pressure, keeping T as constant. So what you will get is del H by del P at constant T, and that will be equal to T del S by del P at constant T. Alright, because T is constant, so obviously this will not get differentiated. The other part, here you will be having what? You will be having V, and you will be having del P by del T at constant T. Okay, now del P by del P. So obviously this particular part will become 1, so you can easily erase this part. So you will be having, this is how you will get your second thermodynamic equation of state. Now this is not the correct, like this is not the final equation. You have to use Maxwell relations over here to substitute its value. just the way we did in the last one. So Maxwell relation tells you that del S by del P at constant T is actually equal to minus del V by del T at constant P. Okay, so you can use this equation, you can substitute it over here, and that's how you will get del H by del P at constant T is actually equal to minus T del V by del T at constant P and plus V. So this is going to be this is called as the second thermodynamic equation of state. Okay, so this is your second thermodynamic equation of state. Now again, you can do it for ideal and real gas, right? The way we have done. So let's quickly do it for ideal gas. So for ideal gas, you know what, for ideal gas we have PV is equals to nRT. So PV is equals to RT, or you can have V is equals to RT by P, right? So you can just substitute, you can just find out the value of del V by del T at constant P. So if I do that, del V by del T at constant P will be equal to R by P, because differentiation of T is going to be 1 and P is taken as constant. So you can substitute it over here. So you'll get del H by del P at constant T is equals to minus T R by P, right? And plus V. Now you know what's the value of RT by P, right? TR by P or RT by P. What's the value of that? That is V actually. So that means you will get minus V plus V, which will actually give you del H by del P at constant T is equals to 0. So for ideal gas, you get from the second thermodynamic equation of a state that the change in enthalpy with respect to pressure at constant temperature is actually equal to 0. Okay, so that's how you can use your second thermodynamic equation of state to find it out for the ideal gas. Now I'm not doing for the real gas, because we'll be taking question based upon that, and then I'll use that particular thing to explain you that how you can get the answer, right? Or you can try it of your own. Okay, the real gas problem, or what will be the value of del H by del P at constant T for real gas, and do tell me in the comment section below that what you guys got. So that will be fun, right? You guys will also be able to understand new things. Okay, now before going into the CSIR-NET, let's take one question over here. So that question says that you have to tell that what is the value of del CV by del V at constant T for ideal gas. Okay, this is the question. Okay, that's the question. Question says that what is the value of del CV by del T at constant, del CV by del V at constant T. So for ideal gas, so let's try to solve this up. So fine, what I'm going to do is I'm going to put the value of CV. Now CV in the previous video I have explained it. Okay, if you have not watched the previous part of this video, you should watch that. Okay, so CV is equals to, you know, du by dt, right, at constant V. That's the value of your CV is. Now I'm going to put that value here. So what I'm going to get is del by del V of del u by del T at constant V, and whole thing is at constant T. Alright, so see, understand what I have done. I have just put the value of CV here. That's it. The rest of the things is like that only. Now I'll apply a theorem called as the Euler theorem. Okay, by Euler theorem. What does that theorem tells me? It tells me that if something is in this particular form, if it's a state function, if something is a state function, and if it is in this form, that is del by del A, if something is like this, del by del A of del M, let's say by del B, so I can write it like this also, that del by del B and del M by del A. That's what the Euler theorem tells you, that you can change the differentials actually. So the same thing I'm going to do, since the things are also constant, so that will also get changed. So I'll get del by del T, okay, of del U by del V, and since it was V, you have to interchange that also. So at constant T and outside it will be go like at constant V will go outside. So you have interchanged the constants and you have interchanged the differential. That's what you have done. That's it. Now, right now only I have seen, like we have observed that del U by del V at constant T for ideal gas was 0, right? Now, since this particular term is 0, so I'll just write down, since del U by del V at constant T is equals to 0 for what? For ideal gas. for ideal gas. That means what? That means that del Cv by del V at constant T is actually being equal to 0. Okay, so this particular term, sorry, yeah, so this particular term will actually be equal to 0 for your ideal gas. So that is something which something new equation which you just got now. All right, so now these were two thermodynamic equation states, and that's how they can be used. Let's take some questions from previous years of CSIR-NET exam, and let's try to see that how you can apply these thermodynamic equation of states to solve them up. Particular question, this is the first question which I will take, and it was asked in your CSIR-NET June 2016 exam. And see, this question was asked for 2 marks, right? So it was pretty simple question and pretty straightforward thing which was asked actually in this video, in this particular question. So how to do this? It says for ideal gas at 300 Kelvin, which of these terms will be equal to 0? Now if you have practiced thermodynamic equation of state, you know, right, that del u by del v at constant T is actually equal to 0 for your this is your first thermodynamic, this equation, like this term comes from the first thermodynamic equation of state, and this is equal to 0 for ideal gas. So without any doubt, without looking into anything, you can just simply answer that option number 1 is your correct option. So it's as simple as that, right? So see, the questions have been asked from this particular thing. Let's take one more question now. Alright, so here in this equation it says that del H by del P at constant T has a dimension of, okay. It was again asked in the same exam, CSI June 2016 exam, for 2 marks. Now, if you know the second thermodynamic equation of state, you know the thing, like you can do the thing, right? So the second thermodynamic equation of state is given by del H by del P at constant T, that's what has been asked, and that is equals to minus T del V by del T at constant P and plus V. Okay, so that is what the equation is all about. By practicing once or twice, you will get to remember this. Okay, you don't have to sit and mug up all the things. Okay, just practicing will help you to remember all the things. Now the same thing about the dimension, which I have just told you just before a few minutes, that if three things are like this, then the dimension of this will be equal to dimension of this, and that will be equal to the dimension of this, right? So that means what? We can say that dimension of del H by del P at constant T is actually equal to the dimension of volume. Okay, why I'm taking volume, why I'm neglecting this term? Because dimension of all the three are equal. We cannot, like, this is difficult to solve, right? Volume is quite simple, you can just see it from directly from here. So you just have to, you don't have to do anything, you just have to write it like that. So it will have a dimension of volume. So without doing anything, just in 30 seconds or less than 30 seconds, you can answer this, that the answer will be option number 2, that is volume. All right, so let's take one last question for this video. And one more thing, I'll just tell you over here that I'll be making a dedicated video on all the questions from thermodynamics. Okay, so don't worry about it. You'll be getting a full-fledged video where you'll be having all the questions which have been asked from thermodynamics in the last few years. So that I'll definitely going to cover. Okay, so but yeah, because we are doing topic specific like videos, so that's why I just thought to include video questions that will just like build up your interest in the topic. Okay, so let's take one more question. All right, so now this equation or this particular question was asked in CSIR December 2016, and it was asked for 4 marks. Okay, it says that the equation of a state for 1 mole of gas is given by this. Okay, this is the equation given to you, where B and R are constant. You have to tell about the value of del H by del P at constant T. So you should, like, it should get click in your mind that from where you will get this del H by del P at constant T. Now the homework part which I have given you in this video to find out for the real gas, just try to do that. Okay, this is not the like absolute equation for the real gas. It's like a different equation from the real gas, but yeah, it's quite similar to that, right? So let's try to do it. So del H by del P at constant T is actually given by minus T del V by del T at constant P and plus V. This is the second thermodynamic equation of state, and this is what we are going to use to solve this question. Okay, so let's try to do what we need. First of all, we need del V by del T at constant P. That's what we don't know. So we know the equation, right? So we have this, just multiply inside. So it will be PV minus PB is equals to RT, or you can say that V is going to be RT plus PB divided by capital P. Okay, so that is going to be the value of V, or you can say that V is equals to RT by P plus B. Okay, this is going to be the value of V. Now what I'm going to do is I'm just going to differentiate it with respect to T, keeping P as constant. I'll just do over here. So I'll be doing del V by del T at constant P. So if I do that, what I'm going to get on the right hand side, R was already constant, P I have taken as constant, so R and P will not get differentiated. If you differentiate T, you will get 1. So that means this will become 1, so you'll just get R by P. And since B is a constant, so differentiation of a constant is 0. So that will be 0, so plus 0, so you don't have to write down again. But yeah, I got the value of it, right? So now I can substitute it over here to get my solution, okay? Or to understand, you can write down plus 0. That doesn't make any sense. So del V by del T at constant P is equal to R by P. I'm going to substitute over here. So when I substitute everything in the first equation of thermodynamics, in the second equation of state, I'll be getting del H by del P at constant T is equals to minus, I'll just put, since T is already there, so T will be there, value of this is R by P, so T R by P, and plus V. Okay, so instead of V, I am going to substitute the value of V. Okay, so I am going to substitute the value of V from here. So what is the value of V? The value of V was RT by P and plus B. Now something is can be cancelled, right? This particular part and this particular part can be cancelled. So what you got, del H by del P at constant T is equals to B. So that is going to be the final answer. See how simple it is, how simple this thing is, and you got equation like option number 2 as the correct option. So in this video, this was very like informative video, I would say. Lot of things have been discovered from the thermodynamics in this equation, okay? And I hope you guys like this video, and if you guys like this video, do tell me in the comment section below. If you want me to improve anything in the video, you can also suggest me that in the comment section below, and that is totally open for you. So you can tell me, or you can suggest me, you can appreciate whatever you want, you can do over there. So I'll just end up this video over here. That's all from my side for this video. I hope this was helpful to you, and I'll be making next part very soon. Thank you so much for watching, and see you in the next video. Till then, have a great day. Keep studying. Bye bye.